Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the Riemann hypothesis. Today's video is another appendix style video where we explain in a little bit more detail a tool that we used on our main journey. In the last video we used a really useful tool called the Abel's partial summation formula, and we did it without much explanation. We just used the tool, and today we're going to look at it a little bit more deeply. What we're going to do is we're going to derive it, which is a little bit of algebra, but before we do that we'll talk about why it's useful, and we'll also finish off with a really nice simple example which shows you the power of this tool. So if you're not interested in the derivation, which is a little bit of algebra, I have to admit, nothing particularly advanced, just a lot of algebra, you can skip that part, but it's here, and it might help if you're struggling with some of the derivations in the textbooks. So just to set out our plan for today, we're going to explain why it's such a useful tool, do a derivation, and then look at a really nice example that really shows off its power. So let's dive in. So the kind of the challenge that it really helps us with is it helps us convert a problem about discrete functions, arithmetic functions, into continuous functions, which are often easier to work with, because with continuous functions we've got lots of tools for exploring their behaviour. We can use calculus, for example. Whereas discrete functions, arithmetic functions, they kind of jump up in step-like ways, and they're not as easy to manipulate and explore, despite natural numbers, normal numbers being a simple concept. So that's what it does. It helps us convert a problem about arithmetic functions into a problem about continuous functions. So that's why it's a really useful tool. So we have to think about what kind of arithmetic function, what kind of discrete function we want help with, and we're going to pick something that's fairly general. So here we've got a sum between two limits, and the sum is only over the integers. So if x1 and x2 aren't integers, then n only takes the integer values between those 2 points. Notice actually this is less than and this is less than or equal to, so that's worth just keeping an eye on. Little detail. So we have an arithmetic function that we're summing over, but it can be weighted by a smooth function. Of course this can be 1 to kind of make it go away, or it can be something that's useful, and we'll find that it is useful. So this is a fairly general expression, and it's general enough to give us lots of applicability, but it's not overly complicated, and it also gives us flexibility in choosing and experimenting how we split the problem that we're thinking about into an arithmetic part and a smooth part. So just to be precise there, arithmetic means it only takes positive integers, n being 1 and 1, 2, 3 onwards. It doesn't take any other values as input. The smooth function, what do we mean by smooth? What we mean is that it has a continuous derivative over this domain. It could be more than that domain, but at least this domain, including the endpoints. So over the area of interest, this smooth function has a continuous derivative. So that's what we mean, just to be precise. And actually an, the arithmetic part and the continuous part, smooth part, can be complex, which is useful for us as well. So let's dive into deriving an integral form for that kind of discrete sum. So as I say, there's a lot of algebra lots of kind of manipulation, but none of it's very difficult. There's just a fair bit of it. So you could see this video as a bit of a reference video, which you can come back to if you're ever wanting to derive it or trying to understand a textbook where some of the steps seem to be a bit opaque. Right, so let's get started. We'll take it slow, we won't rush it. And that's because our aim is to make this area of mathematics a little bit more accessible than some of the textbooks can be. So, because an is only defined over the integers, that sum, the limits x1 to x2, we can clarify those limits because x1 can be real and x2 can be real, but n can only take integral values, integer values. So the bottom, the lower limit, is the first integer just above x1, and the upper limit is the last integer, the highest integer below x2. So we can use this idea of a floor function. So if m1 is the floor of x1 and m2 is the floor of x2, then the lower limit has to be just above x1, so it's m1 plus 1, and the top end is m2. So that's a kind of an easy thing to do. If we drew a picture to kind of explain it, we'd kind of say, here's a number line, here's x1, here's x2, and we can only take integer values along that point. So these are the relevant ones, and if this is the floor of x1, that's the m1 equals, that means the lower limit of that sum has to be m1 plus 1, and over here it is just the floor, which is m2 equals the floor of x2. So this one has 1 added to it because we don't want this one, we want one inside the limits. Hope that's a helpful diagram. Great. Now we're going to make a definition because it's a useful function to have, and it plays a part in the result. And it's this idea of the partial sum of the arithmetic function. So a of x is the sum of the arithmetic function an, all of them up to and including x, where n is integer. So that's a sum, a partial sum as it were, of those an. And it's an observation to say that the an, that term, the anth one, is actually the kind of partial sum at n minus the previous partial sum. That's kind of obvious when you look at it this way, but it's a useful observation that we'll use. So let's write this down. That's the sum that we had from m1 plus 1 to m2, the arithmetic part and the smooth part, and we've just said that an can be written as capital An minus capital An minus 1 in terms of this kind of sum quantity, that thing there. That's all it is. We've just transformed this into this. So that makes it more complicated, but you'll see why in a minute. And then fn is just the same. Now we can expand this out. We can expand out the brackets. So an fn is just that times that, minus this one times this one. Great. What we've also done here is we've just adjusted the n's, reindexed them, so that the an minus 1 here becomes an. So to make that work, we have to shift the limits of the sum. So instead of m1 plus 1, it's just m1, because we've shifted down by 1. So then m2 becomes m2 minus 1. So that's how we've changed from this an minus 1 to an. But we also have to then adjust up the smooth part. The fn becomes fn plus 1. Now, we've done that to make sure that an is the same, so we can kind of pull it out at a future point. The other thing that was going to help us is noticing that these two limits now are different, but they have an overlap. So what's common between them is that they both go from m1 plus 1 up to m2 minus 1, but there's a bit extra from m2 minus 1 up to m2 and m1. Let's draw a picture there. So we have m1, m2, let's remind ourselves what it looks like, m1 plus 1, and the other one was, what was it, m2 minus 1, m2 minus 1. So one of the sums went from m1 to m2 minus 1, is that right? Yep, m1 to m2 minus 1, and the other one went from m1 plus 1 to that one. So there is an overlapping period region, and then we've got the bit extra at the end. So that's the observation we're going to use. So they both cover m1 plus 1 to m2 minus 1. And we can use that to in a way simplify that expression. So we've got the overlapping period, that's the overlapping region, that's for the sum. So it's an fn minus fn plus 1, that's those two combined, recombined, over the overlapping region. And then the extra bits on the end only have, they're only extend by 1. So we have am2 times fm2, that's the bit at the other end, at the top end, and at the bottom end we have minus am1 fm m plus 1. Great. So that's good. As I say, there's nothing overly difficult about it, it's just lots and lots of simple algebra, but we just need to crunch through it. Now we're going to make the key jump, which allows us to introduce the integral. We're going to notice that fn plus 1 minus fn is actually the integral where the limits are n to n plus 1 of the first derivative of f. That's kind of a general statement. So we're going to use that, and we've noticed that this thing here is of that form. It's fn minus fn plus 1. So we can use that over here. We can say the integral from n plus 1 up to n plus 1 from n translates into, and there's a minus there, so this will give us f n plus 1 minus fn, but we've got it the other way around here, so that's why there's a minus. So that's allowed us to introduce the integral, and these are the same terms that we were just carrying from before. Great, so we're almost, we're heading in the right direction. We've got something with an integral, and we've got our original object. Great, we're almost there actually. Now our objective is to just clean up that integral a little bit, simplify it. Now we've got an outside here. If we brought it in, we could call it at, because at is actually n in between these two intervals from n to n plus 1. At is actually an. Remember, that's from the definition of an. So if we move it inside, that's still valid. That's kind of helpful a little bit, but we can do more. The next useful technique is to notice that this is from n to n plus 1, but we're summing lots of these integrals from m1 plus 1 to m2 minus 1. So we've got a sum of consecutive integrals. So we can simplify that into one integral that goes from m1 plus 1 all the way up to m2 minus 1. So we can do that. And that's what we've done here. And the reason that looks simple is because it's n plus 1. So m2 minus 1 plus 1 is m2. And here n is just that, which is there. So that's a nice technique that's used quite a lot. And that's helped us here. So we're getting there. We're simplifying it now, that horrible mess that we had. And these are just, again, the same terms we carried from before. Right, now we need to tidy up a little bit more. Now, we moved our calculations, our algebra, into working with M1 and M2. And that was just, for simplicity. But ultimately, we want to go back to X1 and X2 because that's more general, and that's what we started with. So let's make a general observation, which is going to help us. If we have an integral from x1 to x2, that's the same as going from x1 to m1 plus 1. That's the bit just before m1. So we'll draw a picture to show it. Actually, let's do that now. So we had that term from before, and we said this is m1 there, and this one was m1 plus 1. This is m2. And we're actually interested in x1 to x2, and therefore our integral has to go from x1 to x2, and that is the sum of three integrals which go from m1 to x1. So m1 to x1, x1 to x2, and then from not x2, it's actually up to m2, and then from m2 up to x2. Have I got that right? We've gone from x1 to x2, which is from x1 to... Yep, I made a little mistake there. It's not from m1, it's from x1 up to m1 plus 1. So it's from here. We don't want this region. It's from x1 upwards. So it's the three integrals from let me change colour so it's easier to see. So the three integrals go from here to there, from there to there, and then from there to there. That's what they do. And you can write that out yourselves. It's a useful thing to do, and we can rearrange that. Then we can say we have an integral which is from m1 plus 1 to m2, m1 plus 1 to m2. So if we isolate this one in terms of the others, we just say that plus that minus that is that. That will be helpful for us. Right, so let's do a bit more algebra. So we're just focusing on that m1 plus 1 to m2 integral. There's a minus sign there, and we're saying that is the same as it's the three pieces rearranged. So it's x1 to m1 plus 1, m2 to x2 minus the other one, x1 to x2. That's just this thing rearranged to isolate this one here, because that's the one that's important to us. So that's on the left now, and that's the other bits on the right. And this one then is ax1 of and the limits are fn plus 1 minus fx. That's easy to see. Remember, that's the first derivative. So when you integrate it, it's just f at the limits. And this thing here is the same. It's from x2 minus m1, there's those limits. And the a is x2. The a is x2 or m2 because it's the same. And the same here. because it's constant in that short interval, minus this one here, which we haven't simplified. It's just the general term. Right. Now this integral here, that's what we found in our expression, this thing here. So if we plug this back into it, into that, into the, the expression for the original object, we have quite a long expression. We've got the original terms we were carrying, plus the terms from the latest kind of integral rearrangement, minus this. But we'll end up keeping this because it's useful. So actually, if you expanded this out, this is just multiplying out brackets. There's lots of pluses and minuses. It nicely cancels out. You have to believe me. Try it yourself. Actually, it's not actually that hard. It just looks complicated, but it's just crossing terms out. There's no more manipulation. It's just crossing terms out, pluses and minuses cancelling out. Then we're left with this Abel identity. So we've got there in the end. So that was the derivation, and you may or may not be interested in that, but you might be. But this is a useful identity because it's this general object that we find useful, an arithmetic function weighted by a smooth function, which is a sum over integers in a range, and we've now expressed that in terms of continuous functions. So we've got an integral here, and we've got just the kind of the values at those limits. And in fact, often our lower bound, our first n is 1, which means x1 is say 0. So this thing can often disappear because a of 0 is 0. So let's write that out and see what it would look like. This term disappears because a of 0 is 0, so we're left with the upper limit. And the reason the bottom limit of the integral is not 0, is written as 1 often, is because the at between 0 and 1, but not including 1, is 0, so you might as well start at 1, so that's helpful. So this is often a more practical, simpler form of this identity, but one is just a special case of the other. So that is the Abel identity. That's really, really useful and used quite a lot in number theory. And we're now going to look at an example to illustrate its power. And I have to say, I was quite excited actually by seeing how useful it is. You might look at it and think, how can that be useful? But as I say, it really helps us unlock and explore the behaviour of discrete arithmetic functions by casting the problem into more continuous functions that we can work with. Actually, this AT isn't smooth, isn't continuous because it jumps. But you'll see that when we apply this method, it often isn't a problem. So let's look at a real example. Let's stop waffling. So the challenge that we're going to look at it's almost a familiar series, the harmonic series, and we know by using other methods that were, I guess, more hard work and took a lot of effort, that this thing grows like log n. Let's see if we can arrive at that same conclusion in a much simpler way, and maybe even have more insights. So the question is, how does the harmonic series grow? That's the question. And the Abel identity really helps us with the asymptotic behaviour of discrete functions. That's almost always the go-to tool. So when we've got 1 over n as the series we want to explore, just remember our general object is a arithmetic function times a smooth function. We've got an an and an fx, ax and fx, an, fn. So we have to choose we have to choose what they are, And we've got lots of options, you know, there's almost an infinite number of options, which when an and fn multiply together to give 1 over n. And I guess it takes a bit of practice or a bit of intuition, or just starting with the simplest options. People who do this a lot kind of intuitively know the best ones to choose. But if we choose an is 1, so actually the arithmetic part of the function is just 1. That almost looks like it might not work because it's too simple. And then we say the smooth part is 1 over x. That's what we'll go with, and it will work, but it shows you that sometimes this overly simple configuration still can be very helpful. So if an is 1, the arithmetic function, that means the partial sum ax is very simple. It's just the lower, it's the floor function of x, because this is just counting ones. So when capital A of 5 is just 5, it's 1 plus 1 plus 1 plus 1 plus 1. But if, say, it's 5.5, then it will only be 5. And remember, to use the tool, we need the first derivative of f, and the first derivative of f, when f is 1 over x, is minus 1 over x squared. Again, really easy. So let's plug these things into that expression. So we've got the partial sum on the left. We've got the two limits. We've got an fn, that's the upper limit. We're saying the bottom limit is 1, n is 1. And we then say minus 1 to n of at of the first derivative. I've missed out the dt there. And a bracket. I'll fix that. Now let's see how that works. So an is the floor function, and that is actually n minus the fractional part of n. That's what that is. And then fn is 1 over n. Let's gonna do that pen and paper. That's the floor function. So if I've got so it's like that. The ceiling function is the one that goes over like that. So that's the ceiling function. So the floor function of, say, 5 is 5. It's the greatest integer up to and including that number. So 5.5 is 5. So if I've got x, the floor function is it's actually x minus the fractional part of x. So if this was 5.5, it's 5.5 minus 0.5 equals 5. That's kind of obvious, but sometimes you need to see it. This curly twiddly bracket means the fractional part of. So if we've got an times fn, an is x minus the fractional part of, or n, minus the fractional part of n, and then fn is 1 over n. That's what that is. That's where we got that from. And the same idea applies here. At becomes t minus the fractional part of t, and the derivative is minus 1 over x squared, so that minus becomes a plus, and that's t squared there. And this is what we'll have to work with. So you might think, is this helping? It is, and you'll see very soon that it very nicely becomes useful. So this is just to say, just that reminder that the floor function is x minus the fractional part of x. Now, let's go back and look at this thing here. N over n is 1 minus the fractional part of n over n is something up to and including 1, or up to but not including 1. So it's between 0 and less than 1. So let's write that out. Equals n over n is 1. Well, let's write it really simply. Baby steps. N over n minus fractional part of n over n. So that's 1 minus fractional part of n over n, and that's always going to be that top bit will be from 0 to up to 1 but not including, and that's n. So this is going to be a fraction which in the which we can always say is between 0 and 1, not including 1 but including 0. And as n gets larger, it's more likely to be small, but that's the range it will always be in. It can never be more than 1, and we're going to use that. It's of the order of 1 over n, because as n gets larger, that fraction gets, the top bit will never be more than 1 and the bottom is n, so it's of the order of 1 over n. That's what this symbol means, order of. You can look it up, the more technical definition of the order of, the big O notation, but for the purpose of this conversation, that explanation is fine. So this is saying 1 plus the order of 1 over n. And now let's do the integral. Again, we can split it. We've got the t over t squared, which is 1 over t, and we can integrate that as there. We can do that fairly easily. You can see where the log's going to come from. And then the fractional part. And again, this is always between 0 and 1, which means this is never more than 1. So the integral is always less than, this last one here, is always less than 1 to n of 1 over t squared. Let's write that out. So we've got 1 to n, and we've got that fractional part of t over t squared dt. Now that is always going to be less than 1 to n of 1 over t squared dt, because this thing is always between 0 to 1, not including 1. So it's the order of this thing here. That's the order of that. That thing, and we can perform the integral of 1 over t squared minus 1 over t, taken at those limits, is 1 minus 1 over n. And we can combine these orders of, because order of 1 over n and order of 1 over n is dominated by order 1. So we've got log n, which comes from this integral here. So it's log n plus something of the order of 1. Something that's always, in our case, was always between 0 and 1. That's really helpful. That's really interesting. We've seen already now that this thing, the harmonic series, as it grows with n up to n, it's of the order of, well, it grows like log n plus something that acts like a constant. And that difference between the growth of the harmonic series and log n, that difference is this thing that's of the order of 1. And in fact, if you wanted to kind of look into it more, it's the difference is something called the Euler-Mascheroni constant. It's lots, this is just an approximation, and that seems to pop up in several places in number theory. So that's a useful thing to do there, this use of the Abel summation formula to look at a problem in terms of an integral, and then to be able to sort of extract out how that arithmetic function, the sum, grows. So that's a useful tool, and we use that on our main journey, and I hope today's video has explained both the tool and where it's come from. So I hope you enjoy that. We'll see you next time. Bye.